All right, so good morning. Today we're going to talk a little bit about life after AP Chem. There is. I know. It's shocking. This is the end of your journey. All right, so you have a slip, and a lot of you already have kind of a plan, but I just want to talk about it anyway, so that's where you are now. Hey, congratulations. You can take AP Bio if you haven't already taken it. I know a few of you already took it last year, or maybe you're in it this year. That is simulating a full year of freshman biology in college. And again, you take the AP exam in May. A lot of biology. Basically, a lot of biology. Yeah. Good stuff. You can take, some of you are in AP Physics 1 right now. I think so. Or maybe none of them are actually here right now. They're in AP Physics 1 literally right now. So you do not have to take physics to take AP Physics 1. You're like, wait a minute, could I just take AP Chemistry and not take Chemistry? Nope, it's not organized that way, but for AP Physics, you can go right into AP Physics 1. If you're already in AP Physics 1, you could go in AP Physics 2. But that is going to be a very small class. It has not been offered yet, but it probably will be offered for the first time next year.
Wait, what will?
AP Physics 2.
Oh, okay.
You can take General Anatomy. That is the more advanced anatomy. You get 4 NWTC credits. You get to work with a cadaver at NWTC, which is pretty cool. A lot of memorization. You got to keep up with it. Some of you are in that right now as well. So, I mean, all this stuff, by the way, talk to other people in it. Somebody came up and asked me yesterday if they should take physics or AP chemistry, and just like any of you last year, I never said and never told anybody you should take this or that. I just talk it out. But she was told by a social studies teacher that AP chemistry was the hardest class in the school. Well, yikes. Yes, and I believe that some class that I don't know about either is the hardest class. Talk to the other students. Talk to the other students. They'll tell you. Just like, hopefully, if people ask you about AP Chem, you'll just tell them. I don't have a good barometer on what they're looking for, I guess. AP Environmental Science. That is also a great index. A unique thing with AP Environmental Science is that it is a single semester of college taught in a full year of high school. So you get 1 semester in a full year of high school. Unlike physics, bio, and chem, which is simulating a full year of college in a full year of high school. So it's a little bit different. I don't think you're going to go down this path of potential. Sorry, I shouldn't say that. I knew that was on here. You might want to go into physics. A little less math, a little less intense, depending on your schedule. So that's definitely an option for you. You're probably not going to go into intro to physics. We have a new class starting next year. We don't have lab science anymore. We're breaking lab science down into 2 courses, intro to physics and intro to chemistry, because more and more freshmen are starting to take biology, but we need some alternatives. So you could go into intro to physics. You will not be allowed, oops, oh, I don't have it in here. There's an intro to chemistry. You're not allowed to go into that one. Like the second to last week, you finally are doing element symbols. You're like, yes! It's more advanced than that. It is more advanced than that. You might want to go into earth science if that interests you. Earth systems and weather patterns and things like that. And then lastly, you could decide, depending on your schedule, you could go into basic anatomy. It's a little toned down from general anatomy. Still get 3 credits from NWTC, a little less memorization, but still you kind of get a little taste. So I guess my suggestion to you is you got to think about kind of what you want to do. I always chuckle when people are like, I'm going to do this, and by the time I'm 28, I want to do that, and by the time I'm 32, I'm here. It's great to have a plan, but you also want to make sure that you've exposed yourself to things in case all of a sudden you're like, whoa, I really dig this instead. Keep yourselves open. But if you're interested in going, I'll just say this, like some sort of a medical field, nice to have the opportunity to potentially see a little bit of anatomy somehow, because that's going to be a big part of your life. If you're not sure about sciences, but you know you love it, it's nice to get a taste of all the sciences, so biology, chemistry, and physics. But physics isn't the only other offering, it's also AP Environmental Science. So, anybody have any questions? Yeah, Kevin? Oh.
Okay. Why does it say life after AP Chem when the first one has AP Chem?
I know, because I said...
Again?
Austin, if you keep this up, you will have to take it. I forgot to delete it. Yeah, no, you don't get to choose it. You could audit it, meaning just take it without even grade. No. All right, anybody else with a real question? Still, yeah, Emily. Earth science, environmental science, environmental science goes much more in depth into, that's a good question, into more Earth cycles and systems. Earth science goes also into layers of the Earth, volcanoes, hurricanes, things like that. Environmental science is more about effects on climate temperature and iceberg, maybe thawing. I'm guessing slightly, but carbon cycle, a lot of studies of wind power and solar power, things like that. That's where that goes more. Okay, looks like we got a new toy. So, all right, today we are going to get into our. First, we're going to do a little review. So this sheet is going to go really fast. It was just, it's not that you wasted your time yesterday at all writing down what you wanted to write down. I wanted you to have some imagery. No, just if you needed to make any extra notes, there's one thing we are going to fill out on the side or on the bottom of one of them as well. So on the top, there's not much you really need to write on that one. Again, it's just intra versus intermolecular forces. So reminder. I don't have my normal laser pointer. I don't even know if I can see this. Holy cow. It's about the way that my day is going. See that little thing? Mine's at home. Oh my gosh. The intra are between the molecules, the inter are within the molecules, the inter are between. You might want to just write IMF on the side of this one though. I want to stress that that is an IMF. That is what we're going to be referring to whenever we discuss IMFs. We're discussing intermolecular forces. Again, you have all the definitions and everything already on there. Okay. All right, here is a nice little chart though, and my laser pointer is not working, but we can label it anyway. So this is showing, and this should be on the front page, yes. From weak to strong, and notice it goes from inter all of a sudden to intra. We talked about that a little bit. It says forces between, that's great. Forces within, awesome. So what are the weakest ones that we learned yesterday? What were those called?
London.
London or LD, yes. So what I'd like you to do, right there, write LD or write London. First line, okay? All right, then, as we get stronger and stronger, and what are these again? These are, it's not a big deal to you, but it's kilojoules per mole, so the amount of energy within the interactions. The next line, what did we learn next? What was the next weakest? Dipole, dipole. So now we're getting a little polar, so you can write dipole, dipole on this line. You might want to write in parentheses underneath polar, and you could write underneath LD, nonpolar. Probably a pretty good idea, because that's how you're going to organize your thoughts, is between polar and nonpolar. So we start with nonpolar, we go to polar, and then we're going to go up here actually first. What was that next one? H, bonding, right? If you want to write, you could write really polar, or you could write polar again.
Which line? The top line?
This one right here. Yeah, polar squared. Right now, a few of them we haven't talked about, but in case this comes up, because I want you to be aware of this, and I believe I have an image somewhere, oh, in the lower right. There is a thing called ion dipole. So if you just write ion dash dipole, and sorry, none of this is going to pop up for you right now. So this is ion dash dipole. What you can have is you could have an ionic charged, an atom with a charge, which is an ion, and then a molecule could come around that has a dipole. You could draw, if you want to label the lower right picture, that is ion dipole. That is a huge process when it comes down to dissolving salts. Right? Why? Because the, and if you're like, well, wait a minute, that's hydrogen bonding. Yeah, but it's a dipole. Like, there's a dipole off of that interacting with an ion. You can't have, when you dissolve your salts in your water, you're going to have an ion, you're going to have a polar substance, hopefully water, to dissolve that, okay? And then the last two we learned about, what was the strongest one we learned yesterday? Ions, or ionic, sorry. So if you want to write ionic, or ion dash ion actually would be better if you want to write it that way. So ion dash ion right here.
Ion dash ion.
And then just simply write covalent right here, please. So one thing, and it was my fault, I misled you a little bit yesterday when I wrote covalent and then I put dashes underneath and I made it sound like those are covalent. These IMFs occur in, or between, I should say, between covalent compounds, but an actual covalent bond is an intramolecular force. So anyway, in the notes yesterday, I just want to make sure I clarify something that I think I wrote it out kind of incorrectly, or it was advertised incorrectly, is that the three that we learned, H bonding, dipole-dipole, and London, those occur in covalent compounds, but an actual covalent bond, which is still good on that list. A covalent bond itself is stronger than those other three because it's an intra, but they happen within a covalent bond, so or compound. So that's kind of confusing, I know. All right, we have a couple other images you can label as much or as little as you want. I just wanted you to make sure you had some of these down. So here are the three. Again, if you want to just label some things, the upper left one is just showing ionic or ion-ion. Again, if you're like, I can understand that, that's great. The one on the right, again, that's kind of like the thing on the top, to tell you the truth, is just showing a covalent bond though within. So if you want to write below that, what kind, just the covalent part, is that an inter or an intra? The actual word where it says covalent bond. That's an intra, right? And then the dotted line's the inter, or the IMF. So you could write, just to clarify, like the biggest thing is to start organizing this. And by the end of the week, once we do our labette, you're going to really start to click and start to understand how we approach all this. But we're going to get some practice today. This isn't a very heavy note day today. So you got the inter, you got the intra, and then hopefully you just already labeled this somehow that this is an ion dipole. Here's the ion, here's my dipole. Right? So that's an interactive force. And that's pretty strong. It's not as strong as ion-ion because an ion has a stronger pure charge, but just the same. Please, one little side note, I always like to point this out. How is the water organizing itself to that ion specifically? Why is it all looking like that? Well, the water's polar, that's true. The negative ends are pointing to the positive ion, right? If this was like Cl minus, I hope that we'd expect that the water to all flip, right? And the positive end of the dipole would be pointing towards the negative ion. If you're like, well, I got that down. It's amazing when we actually are required to draw something like that, that we just like, well, I don't know what a salt looks like when it starts to dissolve in water. This is what it looks like. It starts to break apart the ions and the water surrounds it accordingly. Okay. All right, a couple things on the back, and then we'll get into just a couple other notes. All right, I might want to make a little label on this eventually, or just point something out, but I want to just show this to you. And we're actually going to, right now, I'm just going to start it. I have some different compounds. We're going to draw this later. I have water. Oh, shoot. I can't remember. Oh, no. Yeah. Yep, that's it, no. I have water, I did it in the order, ethanol, acetone, and mineral spirits. And what I'm going to do is I'm going to turn them all on to the same number. And we're going to see which one boils first. Okay? But we'll come back to that. It's going to take a little while. Okay? All right, so if you take a look at this, check this out. This chart would be something that would be asked of you to explain, or maybe we take something out of here to explain this. This is boiling points. Note on the top, please, H2O, it's at 100. Water's always boiling at 100. If you're ever on a test and it says it's boiling and it's water, you assume it's 100. You don't say, well, in our lab one time it was 99.1. It's 100 on a test unless if it tells you otherwise. But notice the minute we move forward and you're like, well, what the heck is happening? These are just, this is hydrogen bonded with atoms from different, or elements from different periods. So period 2, period 3, period 4. And then we just move forward with that. So you have H bonded to all the atoms on period 2, H bonded with all the atoms on period 3, and so on and so forth. You'll note after period 2, it drops really quickly, right? The boiling point goes down really fast. right? So what we need to, and what we're going to talk about today is what is actually a boiling point. What is happening with boiling? So what is going on with those three bonds, the high ones? What kind of IMF is that? What did we learn yesterday? H is bonded to all these things. So I guess I'll ask, is that hydrogen bonding or is that not hydrogen bonding? What do you have to do with hydrogen bonding? Oh, I'm disappointed. You have to have, don't you have to have fun with it? Have fun. Have fun. There's F, there's O, there's N. All right, so that's hydrogen bonding. So you might want to circle that. Those are H bonding. Those three. Look how carbon drops really fast. Carbon drops really low. Actually, it's the lowest one. And the reason why, you want to just circle this one, we're going to break this down today. That is CH4. That's a tetrahedral. Is that polar or non-polar? C is surrounded by 4 H's. Non-polar. I'd write non-polar. And then if it's non-polar, what type of IMF is that? LD. Okay. I'm showing you the first steps to this right now. Is that the lower the attractive force, the lower my BP, my boiling point. Okay, the stronger the attractive force, the stronger the IMF, the higher my boiling point. So let's break that down for a second. And eventually we're going to have a couple things in our notes. If you want to do this now, you can start adding this and we're going to just jump back and forth. Here we go. I have H2O. Yeah, I'll do this in order. I'll do it in order how you're looking at it. So I have mineral spirits. I have acetone. I have ethanol. And I have water. What you are going to have to do during this chapter is you need to have an understanding of actual structure. So I know this one. I know water. Actually, I know ethanol too. Water looks like this. This is what your lab at is going to be on Friday with your penny war challenge. Ethanol. Looks like that. Acetone, which is in nail polish remover. Looks like that. It's a ketone. Acetone, ketone. Whoa, mind blown. And mineral spirits actually is a conglomeration of many different. What?
I think I put mineral spirits on the cutting board in this class.
Awesome. It has different lengths of carbon chains. Are you kidding me? It is not on. What? It's on now. There's a little. I'm shorting it out. That's the problem. It doesn't like it. Okay. We'll try that. Let's do one. Okay, so let's break this down, please. What kind of IMF? This is the first step of identifying these things. What IMF is in this? So it's polar, so already I'm out of LD. H bonding. There's an H bond right here. So this is H bonding. Now, what am I talking about? I'm talking about the relationship of one water to another. I'm trying to boil this. I'm separating the waters. I'm separating the ethanols. I'm not breaking them apart. But you still have to look at the bonds within that one because they're going to make attractive forces to another. So the ethanol is unique. Because what do you notice in there?
There's
Anything you notice?
an H bond.
There's an H bond, definitely right here. There's an H bond. But the rest of this would be considered LD. And this is where we need to start kind of approaching different areas. Like, this thing isn't completely polar. It's like there's a part that's polar, and then there's a portion of this that's very non-polar. So yeah, there's some attractive forces, right? Right, polar. And then this is non-polar. Let's make sure we have that kind of a grip on that. Like, okay, so that there's like a kind of a dead side to that, and then a very active side. What about acetone? Is there H bonding? Even though there's H's here, it's not to FO or N, right? But this little area right here does make that polar. There's an oxygen there. So what would I call this one? It's not H bonding, but it's still polar. It's dipole, dipole. And it's because of this right here. Sorry, I know I'm in the way. That's dipole, dipole. Hey, that's still heating. That's awesome. And what about the last one? And either one of those? Very LD. Why? Very non-polar. It's all symmetrical, right? That's what we have to kind of recognize for that. So this is LD, very much non-polar. Oh, we got a boil. This is the first boil. So what does that mean? The highest or the lowest boiling point? Lowest. So there we go. My gosh, this is real time, people. Real chemistry. I'm going to take that one off, though. I don't think we need mineral spirits floating around in here.
Gotta work with the washer.
Such sensitive hands.
Oh, there we go, another one.
Where? Oh, all right, which one? Oh, you're asking us? That is actually, oh, they're kind of going at the same time. That is the, I'd have to smell it. I thought it was the ethanol. Yep, that's ethanol. So we could say this is fourth. This is third. Now, if I ever asked you, like, well, explain a reason why the data's wrong, just understand we always could look for error. These are all on the same hot plate, but they're in 4 different corners. Just like a griddle or anything else, you know, sometimes they're on the pan, sometimes there's a hot spot, or, you know, I'm not sure. I'm using the best hot plate I have. But, and then this one's about to go. I can see it. If you can't see that, it's like swirling. It's gonna go. So this is third, second. So this one would be first. Why? Because it hasn't even gone yet. Does that follow our pattern? Well, let's look at it first. Does the highest boiling point, does that make sense? Yeah. And we're going to talk about what boiling is in a second. But if you want to reach a high boiling point, what you need to do is you need to overcome. If you have a high boiling point, you have very strong IMFs. Very strong IMFs. So you need to put more energy in. And I'm writing this on purpose because I don't want to just dumb this down and be like, oh, there it is, bigger, higher boiling point, higher IMF. You need to make sure you are understanding that we are trying to break them apart from each other, not break them apart. I'm trying to free one, let's say water, from another water. I'm not breaking apart any one of these other compounds, okay? My water still hasn't gone. Let's just quickly bring this home then. This one should make sense that this was the lowest boiling point because it's only LDs. Like, they're very weak. But then here, it's always interesting. It's like, well, that had H bonding. So that should have been stronger. But the problem was that half of the molecule was very much LD. Oh, now it's all going. Okay. Hey, should we just watch this rest here? It's also interesting how things boil. Like this is a really fine boil. This is a much larger boil. It depends on the structure. But because of this whole molecule is polar, because this wouldn't be linear. This would be very much a trigonal planar type structure, but the oxygen would be pulling all the electrons towards it. This one would be the second highest. But if this was, that doesn't smell good. Let's just take that off. Oh my God, okay.
Walks out of the room, cries.
I still have the microphone on. All right, let's get through this so we can do our last part of our notes. So we're going to go back to the boiling point in a second in our other notes, but let's just take a look then. I think I finished this up, but all these other ones are not hydrogen bonding. You have this upper left three that are hydrogen. This is non-polar, and then the rest of these are a very level of dipole-dipole. Okay, and they are higher than the LD, but they will never be as strong as a H bond. So it doesn't take as much energy to separate it. Okay. So just a couple other little things that you might just want to label. You don't have to necessarily. That image is just showing a dipole-dipole. That you saw that one yesterday. It's not a real great extra learning tool, except to understand that, like always, positives are going, opposites attract, similar or same charges repel. And then lastly, we're going to end with this one. This is the LD. This shows LDs. This one, depending on the amount of time I had in each class, we elaborated on it more or not. But this proves, guys, the fact that there's a freezing point, this proves that there are attractive forces. But what these temperatures are showing, and you might want to ad-lib this somehow, is that you have to take almost all the energy out or motion for the attractive force to be able to adhere to another atom. So you almost have zero energy. It takes almost zero energy before the IMFs of the LDs actually kick in. Like you have to have almost zero energy before the IMFs are able to stick. That's another way to think about this too, stickiness. Okay. According to this, helium has hardly any stickiness at all, because you have to slow this down almost to somebody, I can't remember in one of the last hours, actually said it out loud, like, isn't absolute zero negative 273? It's like, yeah, like that's really close. So there's hardly any movement. So there's hardly any stickiness at all. But then as you move down, there gets more and more. One thing though I do want you to add, please put an arrow or something. What's happening as I'm moving down to all of these? With LDs, it's very important to understand. The stronger the LD, it's because of what with the electron cloud. It gets larger. Okay, and you're like, how do you know that? Well, just look at the periodic table. They get bigger. It goes in order on the group, the noble gases. So as you're moving down, the electron cloud is getting larger, and then you probably want to note, if you didn't already, that the LD is actually getting stronger. But that's not an oxymoron, but to say an LD is stronger than another one isn't a huge, giant statement. But it's still important to understand if you're only dealing with LDs. The minute something else pops in, LDs are destroyed, like if there's a dipole or anything else. Yeah. All right, so let's just talk a little bit about boiling, some other things, and then we're going to practice something on our sheet. All right.
I think you're right. How do you hold your pencil?
I'm holding a marker right now.
How do you hold a marker?
with my hands.
You put,
All right, so there's a thing called vapor pressure. Okay, you don't have to stick the water on a hot plate and make it boil for that to all evaporate one day. We know that it evaporates without having to boil something. So we need to understand that process a little bit better. So what we're going to do is just kind of try to simulate this a little bit here. So what happens is you do a P sub vape for vapor pressure. So the P is the pressure. There's always this pressure that's coming off of any liquid. Okay, what happens at an atomic level is at any moment why something evaporates is that the water molecules can get a promotion. So you get these little H2Os and they're floating around, and then one of them at the surface, we'll talk more about this tomorrow, gets to leap and gets to exit. The problem is there's something else pushing back down on it, okay? And that's the atmospheric pressure, ATM. Sorry, you can't read that in the back. That says ATM. Layla, you'll want to write this down. And it's that fight between there, okay? So basically what happens So there's this thing called enthalpy of vaporization that we're going to have to understand a little bit. It's not a complicated thing. Whenever we write enthalpy, it's always something of a mole. So when I put vape, it's just how much energy it takes to basically vaporize or cause a mole of a liquid to evaporate. Well, here's the thing. When I reach the boiling point, if I'm going to have a boiling point, which one has to win? Which one has to be greater? Which one has to be greater to actually reach boiling point? So when this is actually boiling, so all these get to leave all the time. The vape has to be greater than the atmospheric. So if you've ever heard this, or sometimes you don't know how to answer the question, like I don't remember which way it is. You go up in the mountains, you go up to Denver, you're a mile high up, okay? Is that lower or higher pressure? Lower. If you ever can't remember that either, by the way, atmospheric pressure is literally a column from outer space all the way down to you, and all that air sitting in that column sitting on you. So if you're a mile up, you have a mile less of air sitting on top of you, so there should be less pressure on you. It's the same idea when you go into underwater in a pool or whatever. The deeper you go, the more pressure you feel because there's more water sitting on top of you. All right? Well, when you go up to the mountains, what happens? There's less pressure, so you can boil things faster. Okay? That's how that works. There's less pressure, so you can boil it faster. Because it doesn't take as much to leave because there's less pushing down back on it. Okay? So, a couple little last things here, and then we'll get into the worksheet that you have to fill out today. This one's an easy one. All right, let's just quickly. I have one quick image to draw here. Sorry, second. So, I need you to know this. First, the liquid to gas change in state, it always occurs at the surface, okay? I was going to show this as a demo, but it's really lame. I'm going to put some water in and cap it off. Look. So yeah, technically though, the volume does decrease just a little if you quickly close it right then, because there's going to be some natural evaporation, okay? But then what occurs, try the same, somewhat Erlenmeyer, I guess. There's going to be gas particles, and what starts to happen, and this is basically what's called equilibrium, is, and I was going to do 4 lines, 2 up, 2 down, I can't fit them all in there. There's a lot of discussion always about what is occurring once when we have closed containers, or when something reaches equilibrium. Like, why doesn't the water level change? You got to understand, it's not it's not totally stationary. It's a fluid system still. You have water molecules jumping up. They might get bumped a certain way and gain a little bit of energy, and they leave. But gas molecules will also slow down, and they'll come back, and it'll kind of create this equilibrium. So some liquid particles, and this will all help you with your free responses. So what this means is that you'll reach, I'll get out of the way in a second. So you reach this equilibrium, and there's all sorts of different kinds of equilibrium that we're going to be looking at.
What does it say on the bottom then?
Condensation equals vaporization. So, there's a big word here, and I think we're going to end on this today. Huge vocab word. And then we'll practice what we're doing. Volatile. You've heard me say it before, but we haven't really stressed it a lot. It's liquids when they have a high vapor pressure, meaning that arrow pointing off of my liquid is really big. It's really volatile. These are kinds of liquids that you'd smell a lot. Reason why? They evaporate quickly. The definition of it, like, if you're like, wow, that has a really strong odor. Yeah, it's really volatile. It's constantly exiting. This mineral spirits right now, I can smell it just walking by. That's not mineral spirits. That's not either. My gosh. Oh yeah, that was it. Yeah, I mean, you can, if I just set it on any table, or I just dump it out on the table, everyone would be smelling that really quickly. So what does that mean then? Strong or weak IMFs? So that's the key right here, and we're going to box that. Like, if you're able to leave, think of stickiness. Is that going to be strong or weak? Weak. Good, because if it's strong, what you're doing is you're attracted to yourself, and it takes more energy to break off. If it's really weak, oh, that's a really bad color. If it's really weak, then it's not really attracted as strongly to itself, and thus it's not going to stay as a liquid as long. So last 2 items here. If you have a strong IMF, what it means, you have a low vapor pressure. If you have, and I'm just going to throw this out here today because it's going to help you on your labette. If things are really similar and something's really big versus something else, like you have a really large molar mass, that also, like, we get our heads out of science and like trying to be perfect in all the chemistry and the science and just think more common sense here. If something's heavier and larger, it's going to be more difficult to escape. Like, it's going to be harder to jump out. Same concept here. Okay, so larger the molar mass, the more difficult it is. All right, so take a look at this. We got a good solid 11 minutes here. So, oh, jeez. All right, I'm just going to set any of these items. We're going to run out. This is stack. There you go.
The higher the vapor pressure, the lower we do that.
All right.
I said that you should go to the casino more often. Just shut off your ship I'll be playing against you. No, actually no. If I would only gamble and I would only play roulette because I know how to win.
They said they were using the cannon game with this is gonna be the stuff.
What?
Okay, here we go.
Not that way.
We are going to try to identify IMFs. All you need to do, and by the way, no, most people did not get to hear this from me because it got corrected right away. Thank you for whoever returned the Orgo 3 and lesson 33. It was missing from the answer key, so that means the answer key can continue to live. So thank you. All right.
Thank you.
What? Oh. Tomorrow we are going to talk about two other things. So if you want to write this down, this is what you're thinking about. I don't know if you want to write it on the bottom of your sheet or in the middle. There's two other parts. Tomorrow we're going to talk about metals. So if it's a metallic bond, I think we can figure that out. It's a pure metal. And I'll show you that right now. And then tomorrow we're also going to talk about this thing called a network solid. And what that is, like a network, does that sound strong or weak? Like if you were a company and you created this network.
Strong.
It's strong, right? They don't like Verizon and everything else, I swear they say network like 17 times in their commercials because they're trying to show you how strong and populated they are in the nation. So what it is, it's a repeating, well, I'll show you examples though, a repeating network. And usually it's of carbon or silicone. There's no beginning or end. Examples, graphite, quartz, like diamonds. Like it continues, it has all these bonds. It's a network, so it's multiple bonds in different kinds of directions. So we'll address that later. So if you're not quite sure and it has carbon or silicone, just skip it for now, or we could address that. But let's talk about the first couple here. And this goes pretty quickly once you figure it out, kind of the tricks. Number one. It's NH3. So right away, what I have to ask myself is what type of bonding is that? That is not a metal. That is not an ionic crystal. That is not a network solid. Okay? So now I have to go down to, is it basically hydrogen bonding? Is it just polar or is it non-polar? So you do need to know a little bit about it, potentially. And I'll tell you this. It looks like that. So if it is polar, then it could be hydrogen bonding. And usually I'll just say if there's hydrogen bonding, it's probably polar. I mean, that kind of goes hand in hand. Like there's not a lot of, I can't even think of a compound that isn't polar that has hydrogen bonding in it off the top of my head. So is that hydrogen bonding?
Yeah.
Yes, it is. So you X hydrogen bonding. So H bonding. Done. Number two, Kr.
Wait. Do we gotta do anything for the
X,
metal?
just put an X in the H bonding. That's all you gotta do. Kr. So you're like, metal? It's all by itself. Oh, hold on. It's a noble gas. So, and you might want to just make sure you understand what you're doing here. There's nothing there. It's non-polar. So this is an LD. HCl. What is that? H bonding.
No.
No, I'm not having fun. Is that polar though? And you're like, well, it's different. So yeah, that's polar. So this is dipole-dipole. If you want to write it on the side so you understand, that's polar. Two more. Actually, what about F2? It's not a noble gas. Brody, why LD?
It's just by itself.
Well,
It's not, it doesn't look like it has a polar. It's not polar.
yeah, it's nonpolar because F bonded to F would just look like that. It's nonpolar, it cancels itself out. We're actually going to do 3 more. I'm going to find one more like that. So this is LD. What about KMNO4? Ionic. It's potassium permanganate. That's an ionic compound. Oh gosh, I got to remember all that. Yeah, that's a polyatomic ion. That's a metal. It's an ion. It's a salt. Okay, so that's ionic.
So would that be ionic?
Ionic crystal, yes. 2 more. Jumping down to 7. 7 and 8. Please don't mess this up. This is where shapes matter. Okay? I'm just going to bring this up so everybody can see this. If you would do this, and I don't care if you knew there was a bond there or not, that's actually the structure of that. CO2 looks like that. It matters. What is number 7? It is polar, so it is dipole-dipole. Number 8, LD, because it's non-polar. Right? It cancels itself out. Okay? So, you're gonna run into some troubles. A lot of them know you'll be like, I got it, I got it, I got it. Where's the first metal one? Metallic.
19. 17. I don't know, maybe 6, right?
How about 22?
Oh.
22 is a metal. So that's metallic. Silver. So if you're not sure, you know what? The worst thing that happened to you is that you spent about 3 to 7 seconds putting an X in a box, and we can always change that. So circle ones that you're not sure, but I'm not going to elaborate on any more today. And I want you and I need you to bring questions in tomorrow. That's how we're starting the first about 10 minutes of class, is breaking this down. This should be more or less done going into tomorrow. It will be due by the end of the day tomorrow. So you can change that. It's due Thursday. Okay, you're like, whoa, that's really quick. Yeah, you just put X's. Okay, you can do it. We can do it. All right, so you can still work on it. We got, well, I said action. So
Hey, dude, it's supposed to be Spanish, Maryland.